This slide shows a picture here of a point charge, which we denote as Q1, located with respect to an origin, which is here, a distance r1 away. So bold little r1 here is a position vector that goes from the origin to the point where Q1 is located. And we choose to evaluate the electric field due to this point charge at position r here. So we have a position vector that goes from the origin to this point right here, and that's the point where we want to evaluate the electric field. So we write, according to Coulomb's law, that the electric field, a function of bold little r here, is equal to Q1 divided by 4 pi epsilon naught times the absolute value squared of bold little r minus bold little r1. So bold little r is this location, and bold little r1 is over here, multiplied by a unit vector which we'll call a1 hat. And a1 hat is a unit vector which goes from r1 toward r, except it has magnitude of 1. So it's going to be pointing in the direction from the charge to the place where the field is evaluated. And then, of course, as you can see in the expression here, in order to get a1 hat, you would just simply take the difference between bold little r and bold little r1 and divide by the magnitude of that difference, which is written right here. So this is a convenient expression that allows us to place a point charge at a general location given by a position vector r1, and then evaluate the field at another general location given by a position vector r, bold little r. So in this expression we show below, we generalize this so that we can then claim that our charge, which is the source of the electric field here, can be located at any arbitrary point in space with respect to the origin, and we'll call that arbitrary point r prime as opposed to just r1 or r2. And then the place where we choose to evaluate the field, we're going to call that r. And so in the expression, E, a function of bold little r here, is simply equal to Q divided by 4 pi epsilon naught times the absolute value squared of bold little r minus bold little r prime. So bold little r prime here represents the location of the source, which is the charge, and bold little r represents the place where we choose to evaluate the field. And then a hat here is a unit vector which points from the charge to the field point, or to the field evaluation point, and it's given by this expression here. And r here is simply the distance between, or the distance between the point of observation and the point where the source is. So these position vectors are the things that we're interested in understanding how to write down. So the point about position vectors is that they simply allow us to locate a point in space and to track that point. So in this problem, we want to locate what we call the observation points, which are the field points, the place where we want to know the field. And then we want to be able to locate the source points, and those are the places where there is charge or where there may be current. So we have the sources of the electrostatic field, which is the charge, the sources of the magnetostatic field, which will be the current. And what we're going to do is we will use prime coordinates to denote the source locations, and we will use unprime coordinates to denote the observational field point. So if you look at the expression here, a point of x, y, z without the prime would be a place where we want to evaluate the field, and then a point where we have x prime, y prime, and z prime would be a point where we would have a source. And so we're going to use these position vectors in the equations for the electric field in order to specify where the sources are and where the observation points are. On this slide, we show relative to a Cartesian coordinate system, which you can see over here. This is our x-axis, our y-axis, and our z-axis. And I show the 2 points. Here's the general field point, x, y, z. And then here's the so-called source point, x prime, y prime, z prime. And the vector from the origin to the field point is given by bold little r. And the vector from the origin to the source point is given by bold little r prime. And we can write those things in a very general fashion according to these two equations. So give me any point in space, x, y, and z, and a vector from the origin to that point is simply going to be given by x hat plus y hat plus z hat, and the vector from the origin to the source will be written in the same coordinate system as x prime x hat plus y prime y hat plus z prime z hat. So these are just simply two vectors that start at an origin and go out to two different points. One is the observation point, the other is the source point. Okay, and if you look at the picture right here, if I wanted to draw the vector from the source point to the observation point, it would be a vector that would start here and go this way, as I show you here, and that vector is written simply by forming the difference between bold little r and bold little r prime. And if you then do a vector subtraction of the two vectors shown here, you would find that bold r here, big bold R, is going to be x minus x prime times x hat plus y minus y prime times y hat plus z minus z prime times z hat. And then if I want to know the distance or the length of that vector, I will simply take its absolute value, which would then be the big R without the bolding, and then I would just simply plug in bold little r minus bold little r prime. That can be shown to be equal to the square root of the dot product of the vector whose magnitude you're trying to find, and it turns out that would be equal to this expression here. So the square root of x minus x prime squared plus y minus y prime squared plus z minus z prime squared. So that's the distance between those 2 points. Now, the Cartesian coordinate system is useful when you're wanting to represent sources that fit naturally inside a Cartesian coordinate system. So let's say we had a charge that was spread out over a square loop or something like that, then the Cartesian coordinate system would be a natural coordinate system to use. And these two equations right here would be the general starting place to write down any position vector that needs to be specified in Cartesian coordinates. Now, sometimes it turns out that cylindrical coordinates are the best coordinate system because we may have a source distribution